Hello. Hi all. I'm Shravani Vajrapu. I'm working as an assistant professor in TKR Engineering College, ECE department. So today I will explain about 8051 microcontroller. So in the 8051 microcontroller, we, these are the contents. I will tell about the introduction, architecture, pin diagram. I will explain. Before going to the microcontroller, first we have to know about the microprocessor. What is microprocessor? Microprocessor is a single silicon chip. So it has only CPU. CPU contains ALU registers, uh, ALU registers. But we need to connect externally all the timers, output, serial input, output peripherals, ROM, RAM, all we need to connect externally. In the microcontroller, this is a single silicon chip. It have inbuilt CPU, timers, counters, RAM, ROM, serial peripherals, all are inbuilt itself. If we consider example for the microprocessor is our desktops as well as the laptops. If you observe the desktop, we need to connect a printer, scanner, fax machine, mouse. We need to connect externally. But while we consider a microcontroller example is embedded product, the embedded product is used to embedded washing machine. For example, if we consider the washing machine is used for only single purpose for washing of clothes. All the peripherals are inbuilt in the microcontroller itself. So this is the difference between the microprocessor and the microcontroller. Microcontroller Microprocessor and the microcontroller. So the microprocessor we already discussed. Microprocessor have RAM, ROM, input output devices, all the peripherals on a single silicon chip. But in the microcontroller, not in the single chip, but in the microcontroller, we need to connect all those externally, internally. Okay, so microprocessor, since memory and input outputs are connected externally, that's why size is very large. I already told. So for the desktop, we need to connect all the devices externally. That's why the size of the product becomes very large. But in the microcontroller, there is no need to connect any external devices. That's why the size of the microcontroller is smaller compared to the microprocessor. So microprocessors usually used in personal computers. Microcontroller embedded examples are embedded products like used in embedded systems like example uh, TV remote as well as washing machine, TV remote, AC remotes, washing machine, as well as microwave oven. These all are the examples of microcontroller. So this follows the one human architecture. What is one human architecture? One human architecture, nothing but it having only one memory for program as well as for the data. But in the hardware architecture, most of the microcontroller follows the hardware architecture. In the hardware architecture, they have separate program memory as well as separate data memory. For accessing with the CPU, we need to connect a separate program as well as the data memory in the for microcontroller. Like in the hardware architecture, we have separate program as well as the data memory. So there is no power saving modes in the microprocessor, but the microcontroller having the power saving mode. So the cost of the microprocessor is very larger because we need to attach all the peripherals externally. That's why the cost of the microprocessor is very larger, high, while for the microcontroller, the cost is very less. Next, coming to the features of examples for the microprocessor is 8085, 8086 are the examples for the microprocessor. Microcontroller examples are AVR, PIC, 8051. These all are the examples of microcontroller. Next one is the features of 8051 microcontroller. While we are buying a phone, first we are observing the features like what is the ROM size, what is the RAM size, what is the processor, how fast it operates the mobile phone. So similarly for any device that having some features. Here 8051 also have some features. It has 4 8-bit ports. It having the 4 ports. So the 4 ports, port 0, port 1, port 2, port 3. 4 ports are available. That 4 ports are 8-bit ports. Each port having the 8 pins itself. So I already explained how 8051 microcontroller follows hardware architecture. Hardware architecture means it having separate program memory, separate data memory. That's why it having the 4 kilobyte of on-chip program memory as well as 128 bytes of RAM, random access memory. So not only on-chip memory, for example, in our phones we have ROM and RAM. But even though we are adding the SIM card, memory card, because we need extra data, that's why we are adding extra memory. So here also for 8051 microcontroller, we can add a off-chip memory, which is 128 bytes of size. For 128 bytes of size, we can add external ROM as well as the external RAM. There are 16-bit timers, timer 0 and timer 1, as well as 4 register banks B0, B1, B2, B3. 4 register banks are available. Each bank having 8 register R0 to R7, 4, 8 32 registers are available for each for 4 banks. There are 128 user-defined software flags. Mainly, these 805 contains 8-bit bidirectional input-output port, bidirectional bus, as well as the 16 address bus. 8 data bus, 16-bit address bus, but data bus is bidirectional, but 16-bit unidirectional address bus is available. So 32 general purpose registers, each are 32 8 bits in size. So this is about the features of 805. Next, I am explaining about pin diagram of 805. So this is the pin diagram of 8051. 8051 is developed by the Intel Corporation in 1981. This is the 8-bit microcontroller. So this is the 8-bit microcontroller. So here these are the pins. Here 1, 2, 3 and so on, 10 and down to 21, 22, 23 in the U shape, 21, 22, 23 and so on, 40 pins are available. This is the dual inline package because the pins are available on both sides. That's why we called it as dual inline package. If some of the ICs microcontrollers may have flat package, quad package. Quad means pins are available for the 4 sides, that is called quad package. Here it is the dual inline package because our pins are available at both sides. That's why we call it as dual inline package. If you observe the diagram, so these all are the port 1 pins. These are port 0 pins. This is port 2. This is port 3 pins. Okay. I will explain each and every term. First one is the VCC. This is the VCC. VCC nothing but supply pin. Here 8051 microcontroller operates with 5 volts of power supply. That's why. So the by using of 40th pin, here we are giving the 5 volts power supply. Next one is the ground. Here 20th pin is the ground pin. The ground pin is used to connect for the grounding purpose. Here we are using. Next one is the XTAL1 and XTAL2. XTAL1 and XTAL2 are called it as the XTAL1 and XTAL2. XTAL1 is the 90th pin. XTAL2 is 18th pin. So in between XTAL1 and XTAL2, here we are using one quartz crystal. That quartz crystal is used to produce 12 megahertz of clock. 12 megahertz of clock frequency is produced by this quartz crystal oscillator. By using of quartz crystal oscillator only, we can uh, quartz crystal oscillator, we can produce 12 megahertz of clock signal. Otherwise, by using of TTL oscillator circuit also, we can give the clock signals. Next one is the reset pin. The reset pin is used to reset the functionality. Whenever while we are doing the experiments in the lab, sometimes we may do the wrong line, like move a comma r1. We forgot, we may give move a comma r2. At that time we press reset. Otherwise, sometimes the output may not get, we press the reset button. The reset is used to make the program counter to 00H. Means it's start the address from 00H. It removes all the data presented over the what is the previous data available in the circuit. The all over data will be erased by using of this reset button. So reset will be operated in two modes: power on reset circuit, power on reset with debounce. I will explain these two later. So pins of 8051, here we are using the EA bar. EA bar, nothing but external access pin. This is the 31st pin. If you observe, this is the 31st pin, EA bar. So the EA bar is externally accessed. Bar indicates it operates only with zero. Zero, whenever it is zero, it will do the externally access operation. Whenever EA bar is zero, at that time, it is used for externally access purpose. It won't operate for the internal data, internal RAM. Internal ROM is not selected. Only external ROM is selected by using of the EA bar. Whenever EA bar has 1, it chooses internal memory from 000H to 000H to 0FH. But after that, we can also choose, it can also operates for external access purpose also. A bar is 0, then it only access external ROM and RAM for reading and writing of the data purpose. PSEN bar, program store enable. The program store enable is used for the ROM operations, read-only memory. So whenever we need to connect the external ROM, here we need to always connect the PSEN bar, program store enable. For the internal, we have only 6 kilobytes of ROM. But for the externally, we have 128 bytes, means 0000H to FFFH. So whenever while connecting the ROM, while we need to connect the external ROM, so at that time we are using the PSEN bar. For reading, for RAM purpose, here we are using the read bar and the write bar signals. Read bar and write bar are used for connecting the external data. So ALE, next pin is the 30th pin, that is the ALE. ALE nothing but address latch enable. Address latch enable. So port 0 pins are, if you observe, here port 0 pins. The port 0 pins are AD0 to AD7. Address and data both are multiplexed. Whenever any external memory needs to communicate with the port 0, only that memory wants to send the data. Otherwise, it wants to send the address. So at that time, it is demultiplexed by using of ALE signal. Here, ALE is used to here ALE ALE nothing but address latch enable. It is used to demultiplex address as well as the data. So for demultiplexing of address as well as data, here we are using the ALE signal. So ALE is used for it either A0 to A7, otherwise D0 to D7 can be demultiplexed. When ALE equal to 1, it chooses only address. When ALE equal to 0, it chooses only data. Lower order data, ALE equal to 0. ALE equal to 1, higher order data only accessed. There are 4 ports, port 0, port 1, port 2, port 3. There are 4 ports. So port 0, each port having the 8 pins. So all are input output pins. These are bidirectional in nature. Both can be acts as an input, otherwise it can act as the output also. So first I will explain about the port 0 pin. Port 0 pin having the there is no inbuilt both port 0 is used for input as well as output. This is bit addressable as well as the byte addressable. So we can send the data bits. For example, port 0.2 we may use, otherwise 0.3 we can use. Otherwise, we can send the data byte wise. Byte nothing but 8 bits is known as the byte. So port 0.0 to port 0.7 also we can use. Here we are, there is no internal pull-up resistors for the port 0. That's why we need to connect externally 10 kilo ohm resistors. So these resistors are, these resistors are connected pull-up through the power supply VCC. Why we are using the pull-up resistors? I think you got the doubt. So why we are using the pull-up resistors? Without using the pull-up resistors, maybe the voltage may be bounced between either 0 or 5. In between, if the voltage is bounced, at that time the processor can't understand either it is 0 or 1. So that's why we are connected with the VCC. Either maybe it is logic 1, otherwise it may be not connected a logic 0. So inputs and outputs can be understood properly by using of by connecting of pull-up resistors. So pull-up resistor. We already discussed port 0 is address and data, both address and as well as the data are multiplexed by using of ALE signal. We can by using of the ALE we can demultiplex address as well as the data. Port 1 pins. Port 1 pins are just it starts from 1.0 to 1.7, port 1.0 to port 1.7, totally 0, 1, 2, 3, 4, 5, 6, 7, totally 8 pins are available. Both are bidirectional pins, but it won't operate for special functions. So it won't have any special functions, just it operates for only input as well as for the output port. It is also bit as well as byte addressable. Port to 2 pins. Port to 2 pins does not need any pull-up resistors. Like port 0, there is no need, but port 2 having the higher order addresses A8 to A15, totally A8 to A15, total 8 address buses is available. The address bus is unidirectional. Higher order address bus is available at the port 2 of the port 2 of the 8051 microcontroller. Next one is the port 3. If you observe port 3, the port 3 having TXD, RXD, int 0, int 1, timer 0, timer 1, write, read, all are available on the port 3. This is the special function port. So here also there is no need for the pull-up resistors. Here it performs the special functions. So these special functions are RxD and TXD. RxD and TXD are used for serial communication purpose. If we want to communicate data serially to the other peripherals, at that time we are using TXD as well as the RxD. TXD and RXD for accessing of externally data, external RAM. We want to communicate with external RAM with other devices. At that moment, we are using the RXD as well as the TXD. External interrupts. There are two external interrupts. They are int0. Other one is the int1. Interrupt 0, interrupt 1. Interrupt 0 having the highest priority compared to the interrupt 1. Actually, there are 5 interrupts. 2 are external interrupts, 3 are internal interrupts, software generated interrupts. There are 2 timers, timer 0, timer 1. These are 16 bits in size. As well as external memory access also be available by using of read bar as well as the write bar. So this is the port 3.0 pin is used for reception purpose, receiving of serial data, 3.1 for transmission of data, port 3.0 is used for interrupt 0, port 3.3 for interrupt 1, port 3.4 for timer 0, port 3.5 for timer 1, P 3.6 for read operation, 3.7 for writing operation. Here, these pins are used. Next one is the block diagram of 8051. So, block diagram of 8051, the block diagram contains, we already know microcontroller have CPU, timers, count, timer, CPU, bus control, input output ports, ROM, RAM, all are available on a single silicon chip. So here, first main important block is oscillator. Oscillator here XTAL1 and XTAL2. For these two pins, we are connecting quartz crystal oscillator. The quartz crystal oscillator provides 12 megahertz of clock frequency. That frequency is used for operating all the devices synchronously with this frequency only. Without generating 12 megahertz or 11.0592 megahertz frequency, the remaining devices will not synchronize properly. It won't work 100%. So the oscillator circuit is connected to the CPU. CPU nothing but central processing unit. The CPU central processing unit. The central processing unit consists of arithmetic logic unit, control unit, as well as the registers. So arithmetic logic unit ALU contains the ALU performs arithmetic as well as the logical operations. Arithmetic operations like addition, subtraction, multiplication, division, logical operations like logical AND, logical OR, logical NOT, XOR, XNOR, all will be performed by using of the ALU. So next, for that CPU, here we are for this CPU, the interrupt controller is connected. I already explained there are two external interrupts. Those are int0 and the int1. Not only these two interrupts, we again have 3 software interrupts. These software interrupts are generated by the whenever timer 1 or timer 0 are overflow. At that moment, it produces 2 interrupts, as well as for synchronizing of the bus, synchronization purpose, serial data transmission and reception purpose also it produces 1 interrupt. These 3 interrupts also be controlled by the interrupt control. Whenever 2 or 3 interrupts may be occur at the same time, the interrupt control will control based on the priority. So int1 and int0, the int0 having the highest priority while considering with the int1. So the interrupt controller control the interrupts based on the priority. I already told. So a microcontroller is follows hardware architecture. Hardware architecture nothing but it having the separate program memory as well as separate data memory. So here program memory nothing but permanent memory, read-only memory, temporary memory nothing but RAM, random access memory. So ROM is 4 kilobytes of on-chip ROM. Here RAM is 128 bytes of RAM. These all are presented in a single silicon chip. Whenever we need, we can extend up to 64 kilobytes of ROM as well as 64 kilobytes of RAM. There are two timers, timer 0 as well as the timer 1. Timer 0, timer 1, but both are 16-bit in size. Input output ports, there are bidirectional. If you observe here, arrow in two directions, nothing but both port 0, port 2. Why? Because port 0 having the higher order, lower order address and data, port 2 having the higher order address. So totally 16-bit address bus as well as the 8-bit data bus which are connected to the microcontroller. Port 1 is the normal general input output purpose. Port 3 is used for special function like receive RHD, TXD, interrupts, timers, all are connected to the port 3 pins. So I will explain about now. This is the XDAL connection. XDAL. So if you observe, this is the ground connection, 20th pin. This is XDAL1, 90th pin. This is 80th pin. So in between XDAL2 and XDAL1, here we are connected one quartz crystal. That quartz crystal one connected with one of the plate of capacitor. 30 picofarad. We are using it here. We are using the 30 picofarad capacitors. One terminal is connected to the ground. Other C1 capacitor terminal also connected to ground. Here C2 capacitor one terminal is connected to XDAL2. C1 capacitor one of the plate is connected with the XDAL1. So why we are using the 30 picofarad capacitor means the capacitors are used to filter the unwanted signals. So whenever we require 12 megahertz frequency only, at that moment, we need only 12 megahertz of frequency. So that's why the filter will filter out the remaining frequency components present in the circuit. Otherwise, second method is by using of TTL circuit. Also we can generate the 11.059 to 12 megahertz frequency. Here XTL2 is like whenever our laptops, otherwise function generator also generate sinusoidal, otherwise square wave signals. That is also directly connected to the XTAL1. Otherwise TTL circuit also oscillator also produces square wave signal that is given to the XTAL1. And XTAL2 is connected with the no connection. Here, ground is connected with the ground. In this manner also, we can generate the 12 megahertz of clock for the circuit. Next one is the reset. How it operates whenever we are pressing the reset button. So while we are pressing the reset button, so the program counter, what happened in the internal registers of the 8051 microcontroller. Whenever PC becomes, program counter becomes value 000, accumulator value becomes 0, B register becomes, all the values become 0, program status word value 0, stack pointer value becomes 0007 because they have already 0 to 6, all A, B, C, or not to arsenal, all the registers have 8 registers are available. That's why it starts from only 0007. DPTR, data pointer value also becomes 0. So how the power on reset mode and power on debounce mode will operate, I will explain. Here X1, XTAL1, XTAL2 are connected with the quartz crystal. Through the quartz crystal, here connected with the ground. Whenever, without applying any supply, at that moment, capacitor is discharge mode. Reset also be not working. Whenever we switch on, at that time, VCC starts, whenever we are applying 5 volts power supply to the VCC, at that moment, the supply will go through the circuit and RST will be active high. Whenever capacitor starts charging, at that moment, at this dot point, the voltage difference will be occur. Through the resistor, the full current will be flow through the ground. Whenever the capacitor starts charging, at that moment, the VCC voltage will be available at the reset. So in this manner, power on reset circuit will be worked on. Power on debounce mode, here this push button is available at this place. The push button, whenever we are pressing the push button, through the VCC, it is connected to the reset mode. So the reset will be active high. Next one is the registers. There are totally 34 registers are available. In the 34 registers, 4 banks. Bank 0, Bank 1, Bank 2, Bank 3. Each bank having the 8 register. 8 into 4, 8 4s are 32. 32 registers as well as A and B, 33, 34. Totally 34 general purpose registers are available along with A and B. Each bank having the 8 registers. So there is program counter, DPTR, DPH and DPL, data pointer higher as well as the data pointer lower, also available here. Next, program counter. What is the use of program counter? The program counter is while we are doing the experiment. For example, I am writing move A comma R0. Next line is the move A B comma R2. B comma A comma R2. While we are performing the first line, the program counter will hold the address of the next executed instruction. For example, move A comma R0. I am currently executing move A comma R2. So here the address of the second instruction is held by the program counter. Next one is the DPTR. DPTR. So DPTR nothing but data pointer, the data pointer higher as well as the data pointer lower. Data pointer higher as well as the data pointer lower is available. It is 16 bits. That's why it converted into DPH higher, DPL lower. So higher order data pointer as well as lower order data pointer. Higher order data pointer as well as the lower order data pointer. For example, if you want to write A comma, move A comma at the rate DPTR. So move X off. If we write move X, that is used for the RAM purpose. If we write move C for code memory, program memory purpose. Here we are using the move C for ROM purpose, move X for RAM purpose. Here we are using the DPTR. Next one is the A register, accumulator register. Accumulator register. Accumulator register or accumulator holds whenever we are performing a logical arithmetic and logical operations. So all the results will be, most of the operations are performed by using of accumulator. The results are also stored in the accumulator itself. For example, if you add A comma 3 R0. Add A comma R0 here. So here addition of A along with R0. So A and R0 becomes added and the result also stored in the A register itself. So by using of the accumulator register, it performs arithmetic as well as the logical operations. The results are also stored in the accumulator itself. B register. B register, it is also 8-bit register. A also 8-bit register. So here 8-bit register, which is used for multiplication purpose as well as the division purpose. For example, when we multiply two numbers, BA, the result is stored in the form of move BA, mul of A. So whenever we are multiplying A and B, A is 8-bit register, B also 8-bit register. When we multiply both 8-bit register values, the result may be 16-bit. The result is 16-bit. So higher order 8 bits is stored in the B register, lower order 8 bits are stored in the accumulator register. So as well as div A by B. So here quotient is stored in the accumulator, remainder is stored in the B register. Remainder is stored in the B register. Next one, memory mapping in 8051. How it's mapping in the 8051? We know that 8051 have 4 kilobytes of ROM. This is for 8089C52 microcontroller having 8 kilobytes. Some of the Dallas semiconductor have internal ROM of 32 kilobytes. But for the ROM, 64 kilobytes of ROM also be available. So 00000H2 FFFFH. So 64 kilobytes of ROM also be available in the 8051 microcontroller. We can access externally by using of this. This is the RAM memory space. RAM nothing but random access memory, temporary memory. So this RAM occupies divided into 4 banks: bank 0, bank 1, bank 2, bank 3. In the bank 0, 8 register, each bank having the 8 register, 8 fours are 32. 32 registers are available in the 4 banks. 32 into 8, 128 bytes of on-chip RAM is available here. Remaining bits are for bit addressable RAM. Otherwise, some 30H27FH are the scratch pad RAM. So this is the memory mapping for the RAM architecture in 8051. So 00 to 1FH, this is the 00 to 1FH, 4 register banks are available. That is RS1. That banks are chosen by the RS1 and RS0 register. Register select 1 and register select 0. Program status word having the PSW having some flags. 0 flag, carry flag, auxiliary carry flag, parity flag. So here RS0, RS1 also flags. So we can choose the banks by using of these RS1 and RS0. Whenever 0, at that moment it chooses the bank 0, 0, 1, 0, 0. Whenever RS1, 0, 0, it chooses the bank 0, 0, 1, it chooses bank 1, 1, 0, it chooses bank 2, 1, 1, at that moment it chooses the bank 3. So banks are selected by using of the PRS1 and RS0 bits. Again, here 20 to 20FH are the 16 more location, 16 bytes. They are bit addressable as well as the byte addressable. We can use it for either 0, 7, 20, 21. So individually we can use, otherwise we may use it as a byte-wise manner. 30 to 7H for the scratch pad ROM purpose. Here we are using. This is the diagram. Here bank register, bank 0, bank 1, bank 2, bank 3. Without choosing RS1 and RS0, by default, it is 0, bank 0 mode only. Whenever we are enable or disable the banks at that situation only, it changes the banks. Otherwise, it is in the bank 0. From 20 to 2FH, so it is, if you observe 070605, so we can use it as in bitwise manner, otherwise we can use it as a bytewise, like this manner, like in this manner, otherwise we can use single bit order. This is the remaining 30 to 7F, which is used for the general purpose RAM. Bank 0, I explained already. This is bank 0. Bank 0 from 00 to 07, 08 to 0F is the bank 1, 10 to 17 is the bank 2, 18 to 1F is the bank 3. So that is generated by using of RS1 and RS0. We can select the banks. Next, most important topic, that is the program status word. So whenever we are performing addition, subtraction, otherwise multiplication, logical operations, sometimes we may get carry, auxiliary carry, parity bits, overflow. So all will occur, that will be indicated by using of program status word. The program status word is a 8-bit register. So the 8-bit register, it having the, this is PSW 0.0. This is 1, 2, 3, 4, 5, 6, as well as 7. So these 7 are used for the program status word bits. First one is the P bit. P bit nothing but parity bit. 0 dash means this is used for the future purpose. Be nothing but overflow flag. RS0, RS1 are the register bank selectors. F0 is known as the user defined flag. AC means auxiliary carry flag. CY means carry flag. Okay. So whenever carry flag, parity bit, whenever parity bit equal to 1, if the result may be odd number of ones, at that moment the parity bit becomes 1. Whenever the result of the whenever the result becomes even number of ones, at that moment parity flag becomes 0, disabled. Overflow flag. Overflow flag nothing but this is for unsigned numbers and signed numbers. Overflow equal to 1 for signed numbers, 0 for unsigned numbers. 8051 operates for 8-bit micro. This is 8-bit microcontroller. So this range from 0 to 255. Totally 2 power 8, nothing but 256 combinations. But 0 to 255, 255 along with 0, totally 256. So if the value is in between 256, at that moment it is in 0. Otherwise, for signed numbers, it is from 1 to 127, 125 to 127. If the result may be beyond that range, at that moment it produces 1. Auxiliary carry. What is auxiliary carry flag? The auxiliary carry flag is enabled when the result move from higher nibble to the, whenever the carry or auxiliary carry produced from higher order, lower nibble to the higher nibble, at that moment auxiliary carry will be present. After the result of 8 bits, the carry flag will be obtained. I will explain the examples. Here I am considering the example